Prove each of the statements in 10 through 18 by mathematical induction. This is the product from I equals 0 to n of 1 over 2i plus 1 times 1 over 2i plus 2 equals 1 all over 2n plus 2 factorial for every integer n greater than or equal to 0. So the first step is always the same in that we need to identify our statement p of n. P of n can't include any quantification, so we need to be careful here and say that this right here is p of n. Now keep in mind this equals p of n, but notice how this equals is different than that equals. So this equal symbol here is the double equals, which means that the left-hand side is equal to the right-hand side. And this is a logical operation, meaning that the output of this statement is either true or false. So P of n is defined by this statement here. So I just mentioned that just so that you can understand that there's a difference between these two equal symbols in the role that they play. All right, now that we know what our statement P of n is, let's start with the base case. So this is the smallest integer n such that P of n is true. And in this case, we want to show that the statement is true for every integer n greater than or equal to 0, which means that our base case is going to be n equals 0. So let's first figure out what our statement P of 0 is. Our statement P of 0 is that the product from I equals 0 to 0 equals 1 over 2 times 0 plus 2 all factorial. Now I'm going to put a question mark here just so that I don't accidentally assume the conclusion that I'm trying to show. I want to show that these two things are equal to each other. I want to show that this statement is true. And in order to show that this statement is true, what I'm going to do is I'm going to evaluate the left-hand side and I'm going to evaluate the right-hand side separately and show that we get the same result. So let's start with the left-hand side of P of 0. Now in this case, the index variable I varies from 0 to 0, meaning that the starting place for our index variable is the same as the final step in this product. So there's only one factor in our product corresponding to when I equals 0. So I'm going to substitute I equals 0. So I get 1 over 1 times 1 over 2. And this is the only factor in the product. And we can simplify that to just 1/2. So that's the left-hand side. Now let's look at the right-hand side. And let's see if we also get 1/2. The right-hand side of P of 0 is 1 over 2 factorial, which is just 1 over 2. And so the fact that both the left-hand side and the right-hand side are 1/2 for P of 0, then that means P of 0 is true. So next, let's move on to the inductive step. So let's instantiate k to be an arbitrary integer such that k is greater than or equal to 0. And we're going to assume that P of k is true. So the first thing I want to do is I want to define what P of k is. This is the thing that we get to assume is true. So P of k is the same as the statement P of n, but we replace all of our n's with k's. So this is my statement P of k, and we get to assume that this is true. Now the reason why this isn't circular reasoning is because k doesn't represent every integer. K just represents one arbitrary fixed integer. And so we're assuming that P of k is true for specifically this arbitrary integer k, not just for every single one. And the goal is to show that P of k plus 1 is true. So I'm going to put, we want to show, WWTS, that P of k plus 1 is true. So let's detail next what it is that we want to show. Our goal is to show that the product from I equals 0 to k plus 1 equals 1 over, this is going to be 2 times, instead of n, I'm going to write k plus 1, and then plus 2 factorial. This is what we want to show. So we want to show that the left-hand side of this thing equals the right-hand side of this thing. To do that, we're going to start with the left-hand side of P of k plus 1, and we're going to do stuff to it using the inductive hypothesis, which is P of k. So let's write that the left-hand side of P of k plus 1 is the product from I equals 0 to k plus 1. Okay, so now this product looks a lot like the left-hand side of P of k. It's just we have this extra term at the end. The index variable I varies from I equals 0 to k plus 1, not I equals 0 to k. So to fix this, what we're going to do is we're going to rewrite this product in expanded form. So I'll start with plugging in I equals 0, then I equals 1, then I equals 2, and then we'll write out the last 2 or 3 terms. So when I equals 0, this is 1 over 1 times 1 over 2. When I equals 1, this is 1 over 3 times 1 over 4. The third term is going to be 1 over 5. That's when I equals 2 times 1 over 6. And then all the way to, I'll write the second to last term, which corresponds to when I equals k. That's the second to last term. So that's when I plug in I equals k. So that's 2k plus 1 times 1 over 2k plus 2. And then our last factor corresponds to when I equals k plus 1. Okay, so let's write this product in expanded form. So let's plug in I equals 0, I equals 1, I equals 2, all the way up to I equals k, and then I equals k plus 1 at the very end. So when I equals 0, this is 1 over 1 times 1 over 2. When I equals 1, this is 1 over 3 times 1 over 4. And then when I equals 2, this is 1 over 5 times 1 over 6. And this keeps going all the way till, we'll write the second to last term, which corresponds to when I equals k. That's the second to last term here. The last term corresponds to when I equals k plus 1. So that would be this last factor here, and that's the last factor. Okay, so the strategy here is to focus on the first k terms of this left-hand side. If we rewrite this product by pulling out this last factor from the product, we'll be able to utilize our inductive step. So I'm going to rewrite this as the product from I equals 0 to k, and the formula for each of these factors is still the same. It's still 1 over 2i plus 1 times 1 over 2i plus 2. So that's me rewriting the first k factors here, and then we also have this k plus 1th factor that we have to keep in mind, which I'm going to rewrite as 1 over, this is 2k plus 2 plus 1, which is 2k plus 3. And then 2 times k plus 1 is 2k plus 2 is 2k plus 4. So this is what I get when I pull out the last factor from this product. So now I can rewrite this product using the inductive step. Let's go back to the inductive step real quick. If you notice, the left-hand side of my inductive step is exactly what we have here in purple. And so we can rewrite this left-hand side of p of k as the right-hand side of p of k, which is 1 over 2k plus 2 factorial. So I'm going to rewrite this as 1 over 2k plus 2 all factorial. So before we move on, I want to emphasize here that you need to justify this step by saying by the inductive hypothesis, or by IH. Without the inductive hypothesis, we can't reach this step. And it's important to know that when you use the inductive hypothesis, that means that you're just a few steps away from showing that p of k plus 1 is true. So this right here is just a few steps away from the right-hand side of p of k plus 1. What I'm going to do is I'm going to combine all of these three fractions into one fraction. And I'm going to reorder the multiplication just a little bit. I'm going to write this as 2k plus 4 times 2k plus 3, and then times 2k plus 2 factorial. And that's all under 1. This is the same thing as 1 over 2k plus 4 factorial. Now let's explain why that is a little bit further. Just as a side note over here, 2k plus 4 factorial can be written in many different ways. We can pull out the first factor, which is 2k plus 4, and rewrite this as 2k plus 4 times 2k plus 3 factorial. And then we can keep pulling out terms. We can rewrite this as 2k plus 4 times 2k plus 3 times 2k plus 2 factorial. We can even write it as 2k plus 4 times 2k plus 3 times 2k plus 2 times 2k plus 1 times 2k factorial. So there's lots of different ways of pulling out factors from the factorial, but this is just one way of rewriting 2k plus 4 times 2k plus 3 and then times 2k plus 2 times 2k plus 1 times 2k times 2k minus 1 and so on. And we can just write that as 2k plus 4 factorial. And this is the right-hand side of p of k plus 1. And so let's pause and recap what we just did. We started with the left-hand side of p of k plus 1, and we showed that that equals the right-hand side of p of k plus 1 using the inductive hypothesis within our inductive step. So this proves that the statement p of n is true for all integers n greater than or equal to 0. Thanks everyone, and I'll see you in the next video.